Welcome to another episode of AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. In this episode, I'm joined by Sid Sheth, CEO of D-Matrix, to explore one of the most important shifts happening in AI today, test time scaling. While most people think progress comes from training ever larger models, Sid and I talked about how today's models think more at inference time. We talk about why reasoning workloads are driving a big explosion in demand for tokens, about how memory bandwidth is the bottleneck, not compute, and what it takes to build affordable, real-world inference hardware that can handle bursty, interactive AI applications. From distilled models and multimodal reasoning to chiplets and in-memory compute, this conversation connects where AI is headed with the infrastructure we need to get us there. Here's my conversation with Sid. Okay, here at D-Matrix with Sid Sheth. Welcome to the show.
Thank you.
So we're going to talk about test time scaling today. Maybe you could start with something like, for people who haven't really heard about this, they probably are familiar with test time scaling, they just don't know that we call it that.
Yeah.
And what do we mean by test time scaling, and why do we need it?
Yeah, so that's a great question. I think, recently, at least I want to say probably in the last year or so, test time compute, test time scaling, inference time compute, all the same thing.
Same thing.
And, really the fundamental idea there is you want to be able to throw more compute at inferencing a specific query. And what is very attractive about test time compute or inference time compute is the fact that here you have a model that is trained to do reasoning.
Yeah.
And can reason queries that it might have never seen before, right? So you're essentially trying to get to answers to questions that you've never seen before based on what you've already been trained on, because you've learned the ability to reason through questions and the ability to reason through data. And that is obviously a super attractive area because most of the AI models out there today are one-shot thinkers, right? They either know the answer to the question they've been asked, and that's purely a function of whether they've been trained on that or not. Or what if you could ask a question that is not a one-shot, a single shot, or a system one kind of question, a system two thinking question, which is more about really more abstract. And the model still understands the intent of the question, can reason through different possibilities, and eventually arrive at the right answer. But that just means you need a lot of compute. You just need a lot more compute, and you want to do it quickly. Your turnaround times matter, so latency matters. So suddenly things like having enough compute accessible, but also being able to do it with high levels of interactivity become very, very important. And it's a super exciting direction about where AI is going with that.
So the whole aim is really to get smaller models to behave as well as the bigger models do, right? I mean, it works, doesn't it?
Yes, that's exactly the idea. You typically start with a bigger model. What they do is they'll have a frontier model that gets trained with those capabilities. And, you essentially want to figure out the solution space of what's possible.
Yeah.
And you say, okay, great, this is what's possible, but I don't really need all of that. And then you want to kind of scale down from there, depending on, a certain class of problems or whatnot, right? So you have to focus on math problems, or you want to focus on legal or some specific domain, and you can distill models down to specific areas of expertise, because not everybody needs access to everything all the time. Right. So you figure out, okay, this seems like a vertical where, people would love to use this in the context of, solving a bunch of math problems or solving, whatever other type of problems you want to solve, and distill it down to that solution space. And those models tend to be a lot smaller, a lot more efficient to run on hardware, and they are just as capable in that specific area of expertise, right? So I think that's certainly becoming a huge trend post DeepSeek. I think DeepSeek was really when, there was the first time people appreciated the importance of taking, larger models, distilling them down and saying, oh, wow, this is actually just as capable for everything that I need.
Yeah.
And so this is becoming a real trend moving forward, right? Which is, and when it comes to inference, it's super important because, cost matters and latency matters, and smaller models are, tend to be more cost efficient and latency optimized.
So with techniques like reasoning, the basics of reasoning or the basics of this are like, let's just do 3 inferences of the same thing, compare them and pick the best one. Yeah. Some of these techniques are almost like heuristic techniques, right? It seems like a bit of a cheat, in other words.
Kind of, except that I think the models now can spawn multiple chains of thought, right?
Okay.
Yeah, so they can go off and actually, go down a path and say, okay, what is, reason down a path and across multiple paths, and eventually get to an answer that, and then yes, there is some kind of an algorithm there that eventually will, figure out which answer is the best answer and kind of present it to the user, which you may not like, in which case you can force it to reason again on a totally different vector and different chains of thought, right?
Yeah.
And eventually converts to the right answer. But again, that goes back to, really having the ability to kind of turn this around in a very short amount of time, because these questions are getting more and more abstract. I mean, there was one example, somebody was saying, like, okay, if I asked, you the question, what's the capital of Mozambique? You probably know the answer to that question, yes or no. If I asked you, what does the fiscal policy of Mozambique need to be to, do more trade with the, EU? That's a very abstract question. Even if you present this to a bunch of humans, they'll probably have to go off for a week and come back, with different responses that they may not all agree on. And then somebody, somebody with higher authority would probably have to look at all those different responses, pick one and say, okay, this is the path we're going to take. So in that sense, reasoning models are not very different. Probably they don't need a week to do all of that work, right? And you don't want them to take a week. Can this be done in a day, maybe a few hours, right? And maybe present a response. If you don't like it, you try again, right? But yes, it is heuristic to a certain level, because, if you don't like the responses, the human can force the model to go down a different path. So in that sense, yes. But the model is actually reasoning through different possibilities and coming up with, what it thinks could be the best response.
And some that I've seen are like, it shows you the reasoning as well, or it shows you its chain of thought. But I guess if we could make it even super fast, we wouldn't need to see the chain of thought. It would just pop up with the eventual answer.
I think so. One of the reasons, at least the earlier models presented that option to users, was, I think, it's just kind of building trust, right? Like, how do I know, first of all, why do I trust the answer that he came back with? So here, I'll show you all the steps, that tell you how I reason through getting to that solution, right? And then you can decide for yourself whether you like, the steps I took. If you don't, then you can force me down a different path and I'll show you something else. Now, I think post DeepSeek, I don't know how much of that will be available, because I think what happened as a result of that is basically DeepSeek was able to, take, those steps and exactly understand how OpenAI does. The one model was doing all its reasoning, and they were able to emulate that. And, it became a bit of a issue for OpenAI in that, like, look, we lost our competitive advantage in the process. So moving forward, I've not seen too many of these models actually, spell out their reasoning steps, at least the ones that have been available of late. But I think it's always good to have that option, I think. And I think my sense is the open source models will always have that. The closed source probably not so much, because if your business is entirely predicated on having the best model, then you don't want to kind of put that out there. But if your entire business is on making the model available to as many people as you want to, then you want to build trust, and then you want to make that available. So I think that is where the bifurcation is most likely going to happen.
Okay. I hadn't thought of reasoning techniques being like a big differentiator for these guys, but of course it affects how well the model works by multiples, right?
Right. And then that, you can, exactly, and because there is a lot of learning in that, and you can then incorporate that into your way of, how you kind of train your model, right? So you're a competitor trying to build a model that, and your business is predicated on being the best, then you could learn from that and, go off and do similar things, right? So.
Oh, yeah. Okay. What about for workloads that aren't text, or that isn't an LLM, maybe multimodal, maybe imaging? Does test time scaling apply here too? It's not really reasoning in that case, but what test time scaling is coming to multimodal models?
Well, I think it should apply. I would think so. Like, let's take a simple example of video, right? So video is one of those classic examples where you want to prompt the model and you want to generate, video content, and your prompt will be pretty abstract, right? Right. And so right now, first of all, video generation in general is not real time. And eventually we think it is going to become real time. By the way, we'll talk about that in a little bit. The hardware that we are building is really targeted for real time video gen. But strictly from a reasoning perspective, no, I would think if you're anything that has a highly abstract prompt that you want to kind of break down and get to an outcome, reasoning is something that you could use, or test time compute is something you could use for that, because essentially you want to spawn multiple chains of thought and figure out, different possibilities.
Yeah.
It's a solution space. It's just expanding the solution space of what's possible, and you want to try out different approaches. So test time compute is actually great for even multimodal, content generation of any sort. So I would expect probably more popular for multimodality,
Yeah.
especially if you're trying to create a video and you want all the different options possible and you want a larger solution space. Great. I mean, I would expect that's going to be more popular for multimodal.
I mean, the ultimate effect is we're going to need many, 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 many more times the amount of tokens, which is great news if you're selling inference hardware. I know you've spoken about, how we need really fast latency for this to do too, but is it like we can get away with less training on the kind of pre-training side by compensating doing these reasoning techniques in the inference side using inference compute? Or do you see that as something that's coming, or am I going in the wrong direction completely?
That's a great question, right? I mean, I think, and again, I don't know the answer. I'm just I'm postulating here that this is, because I think we've been on this vector for the longest time that you want to train more, right? And now we're kind of getting to that point where there is another way, right, with test time compute, where you say, look, I don't need to, instead of training more, why don't we get the model to think more?
Yeah.
Right. So we have this thing at D-Matrix, we say, think more versus train more, right?
Yeah.
And it's not entirely clear that the results are going to be exactly the same, right? So to be seen, but I would argue just, if you were to ask me, my hunch would be that is where things will go. It will go towards, why don't we get more efficient in terms of how we get the models to think more? We don't, you pre-train once with a very large amount of data and takes you forever, and it's getting harder. I mean, just look at what's happening with Llama Behemoth, and it's they're just eking out gains from these models beyond a certain point is getting incredibly hard.
Absolutely.
Right? And maybe there's a better way. You just take a Maverick or a Scout like model and you get them to reason more and think more, and they might surprise you. Is all I'm saying. And I don't think there's enough data to say one way or the other.
It's just an interesting thing.
I think my hunch would be that that's the direction things will go. Is getting them, getting models to think more and just do more test time compute.
If everybody adopts reasoning models, which it looks like most applications will, or at least from my perspective, it looks like most people will, do we need 2x the amount of tokens, 3x the amount of tokens, 10x the amount of tokens? 100x the amount of tokens for reasoning. It's really as much as 100x.
I think so. It'll go there very quickly, right?
Okay.
Because again, I think it's a function of, human beings, they'll always find a way to use the compute that is available to them and write applications to totally tap into any amount of compute. So I think it's going to be strictly limited by cost.
Okay.
Right? It's going to be cost driven. So if the cost curve comes down faster than the amount of compute available, then people are just going to just do 100x the amount of tokens, and whatever the number is. It could be 1000x. I don't know. You can throw a number there. But I don't think it's going to be gated. I don't think it's going to be like, I don't think we need anything more than this. So they'll find use cases that will need more than that as long as the cost permitted, right? So I think that's what we are focused on. Is like, okay, what does it really take to build a world in which people go to that think more versus train more world where, look, I'm going to only pre-train so much. I'm just going to solve all my other problems by just getting this thing to think more. And as long as I have as many thinking tokens available as I can, to solve, any question that I have, well, then guess what? If it's cost, then what kind of solution, what kind of architecture do you need to build to drive, the number of reflection tokens or thinking tokens up by a factor of 100?
Yeah.
Right. And what is it fundamentally that is preventing us from getting there today? And that is what really we are focused on solving, right? And yes, it's compute, but actually you realize quickly it's not just compute. It's memory bandwidth, right? And that's really the choke point and the bottleneck. And are there creative ways to solve that problem so that folks can have access to plenty of thinking tokens?
What are some creative ways to solve that memory bandwidth issue?
So exactly. So I think so the first thing we did was, and this was a little bit of insight, a little bit of luck. When we started in 2020, there were no reasoning models, and there was no inference for that matter. That people were not really talking about inference as much either, right? Certainly no LLMs. Certainly no generative AI, right? So I think the models that we were looking at the time was model like BERT and ResNet, and the only thing we knew was GPT-3 had just become available, right? And this was a 175 billion parameter model. It was the largest model of its time, and given where the NVIDIA hardware was at the time, the GPU hardware was at the time, this was a very large model, right? And you couldn't fit it on one card, and it was becoming very clear that to run this model effectively, you needed access to a lot of memory because of course the model is big, and you have to shard it, and the performance, and it's a generative model, so token generation was strictly a function of access to memory. So we said, yeah, that's interesting. And I said, okay, if the trend continues, okay, we are on GPT-3, then GPT-4, and the models keep getting bigger, then this is only going to get worse, right? So we should go solve for that problem, which is the memory bottleneck problem. And how do we take a GPT-3 model? We don't want to put it into a DDR type of memory because it's going to be really slow. So what class of memory do we need to go create to get this to fit in that class of memory? And then that would really kind of solve the choke point. And that's how we came up with in-memory compute. And we said we're going to just, we're just going to conflate, or basically we're just going to collapse that first tier of memory hierarchy into the computing. Right. And so we don't have this tiers, tier one cache, call it. It's all collapsed into one compute array where we keep the model. So we just make fewer trips to memory. We still have a cache on chip, but we make a lot fewer trips to memory. And that was the first basic idea we had, which is okay, look, this is great. Let's start here. But then SRAM, has not continued to scale the way other things have, and models just got so big that we quickly ran out of SRAM space. So we then said, there's probably another way to do this, and then we kind of are migrating over to kind of stacking DRAM memory on top of compute. And now we kind of move away from that SRAM scaling problem. DRAM has a lot more capacity. And the technology to stack multiple layers of DRAM on top of compute is already available. And so now we can keep pace with the size of growing models. There's a couple of things that happened. One is we found a way to increase capacity. But then folks also found a way to distill models.
So they're meeting you kind of where you are.
So we are kind of meeting each other, at the midpoint. And it's kind of nice because now we can keep scaling as the distilled models keep getting bigger. We have technology that is, capacity in memory that is big enough to accommodate all of those distilled models. And the more important thing is we solve for the memory bandwidth problem, which is essentially once you put memory directly on top of compute, we are essentially dropping data from the memory on top directly onto the compute tile through either it is micro bumps, right, TSVs, much higher bandwidth, because we just have a lot more connections than a chip that is placed sideways. HBM connection just even through a silicon interposer will just not have that many connections. As versus kind of going this way. That's just physics, right? Simple to actually visualize things in a planar domain versus 3D. So we are almost 10x. In the 2027 timeframe, we'll be 10x the bandwidth of HBM, right? So HBM5, which is not available yet, will be 13 to 14 terabytes per second, and we'll be north of 100 terabytes per second.
Wow.
Right. So, and HBM will just not be able to catch up with something like this in our time frame, right? So I think we'll always be multiple steps ahead, and I think you have to build this from the grounds up because you can't really stack DRAM on top of very power hungry GPUs because DRAM's very thermally sensitive. And so you got to build a platform that will allow you to do that. And our approach with chiplets, where we build these chiplets that are max 50 to 100 watts, right? And now stacking DRAM on top of that becomes a lot easier. And as opposed to stacking DRAM on top of a very large chip, we kind of break the compute into tiles, and then we stack DRAM across those multiple tiles, and we can still fan out. We can go high and we can go broad.
How high can you go?
So we can, it's like, there's really we can go like HBM goes 12 stack high, and over time this will go 8 to 12 stack high, right? So we can just keep going as the technology matures. So that's the roadmap. Our roadmap is essentially we can go broad with chiplets, and then we can go high with chiplets. And with that approach, now suddenly solve the memory capacity problem and you solve the memory bandwidth problem. And compute is not the biggest problem. It's like we have enough compute on these tiles, we can keep pace, but that is not where the primary choke point is. It's just, for the prefill phase and prompt, processing, yes, you need compute, but there's enough compute with this approach. It's not like we need to kind of over-index on the computing vector. I think we need to optimize on memory bandwidth and memory capacity vector and find the right balance between compute, memory bandwidth, and memory capacity, which is what we did with this platform.
Yes, yeah.
And you got to build it from the grounds up. You can't really build this as an afterthought, right? And then software has to kind of work with this approach. It has to scale across these chiplets, and you could have a card with 4 chiplets and then 8 chiplets and then 16 chiplets, and the software should be able to keep pace with that. So you got to build everything from the grounds up. It can't be like, oh, I want to do this once you've gone down a different path. So
exactly.
I think we're going down the right path here. And coming back to the original question, which is why is this good for reasoning, which is exactly this. Is now that we have this capacity and we have all this memory bandwidth, we can keep a lot of those thinking tokens, as the model is thinking through this stuff, it is generating KV caches.
Yes.
For those responses. The KV cache size is kind of ballooning as it's doing more reflection.
Yeah.
And then we go back to the things like if it's 10x, 100x. Well, we think we can go to 100x because now suddenly we have all this capacity where we can keep all these thinking KV caches in DRAM memory. And that is what allows us to really kind of change the game on how reasoning would be done in the future.
Okay, you're one of the earliest adopters of chiplets that I've seen. You've got your chiplets on an organic substrate.
Yeah.
And I know one of the reasons for that was cost. How important is affordability to the whole solution?
And when you say affordability, you're talking about affordability to the customer, right?
Yeah.
So, yeah.
Well, I mean, and then on to their customer, I suppose.
Onto their customer, yeah. No, it's super important, right? I mean, so every decision, by the way, we've made here is with cost in mind, right? And so things like chiplets and, so they yield better, putting them on organic substrates, it's cost effective. We don't want CoWoS, we don't want silicon interposers, we don't want HBM, using LPDDR memory versus HBM, using, SRAM and DRAM stacking versus HBM.
Yep.
All these techniques, we had to essentially circumvent a pretty large part of the ecosystem to, figure out how to build a solution that is cost effective and is available.
Yeah.
Right. So the other thing is you go solve for the cost problem and you go build something esoteric that is not very readily available, and then you have another problem, which is you can't really supply enough product to customers, or there's just not enough volume behind it. So how do you create a solution here which is supported by large enough volume? So LPDDR is supported by mobile DRAM volume, and organic substrates are organic substrates, high volume to be right. Chiplets, the technology is there. It's certainly not esoteric anymore. I mean, right, and then packaging all this up, using the way we put it together. There is nothing that we do on this product here that doesn't run through a high volume supply chain. Even the DRAM stuff, we talked about DRAM stacking.
Yeah.
The DRAM stacking problem, interestingly, was solved a few years ago by the crypto guys. They were the first ones who really needed access to high bandwidth memory, right? And they were having the same problem as essentially they were not getting access to enough HBM memory. So they went and solved for this problem, a few years ago. And it really never got commercialized because of the crypto bust in 22 and 23. So this technology just sat there. And till folks like us went in and said, there is another application with AI that also needs access to memory bandwidth, and why don't we go commercialize it, right?
Yeah.
So again, there is volume that has run, there is enough volume that has run through that and will run through that we think, cost-wise and affordability-wise, this is a solution that is going to be very competitive.
Okay. Yeah, I got it. So crypto is useful for something.
Exactly.
I'm kidding. Okay. One of the things we've spoken about before, which I feel we really should mention, is this idea of like real world use cases. So when we spoke about this before, we were talking about batching, we were talking about bursty user demand, mixed content lengths, all these things which make it difficult to deploy in a performant way. Yeah. Tell us how you deal with customers' problems on that front. How do you solve customer problems on that front?
That's a great question, by the way. So I think, that's, if you look at, there's two extremes we think in the market right now, right? I mean, there's a lot of folks, some of our startup peers focusing on kind of batch one inference, and, that's great for, benchmarking and whatnot, right? But real world use cases don't exist there, right? And then there's the other extreme, which is GPUs, which is, like highly batched throughput, right? And this is, batch sizes of 500 and up and whatnot, right? Yeah. But when we have customer conversations, like pretty much every customer tells us that they don't have enough users to simultaneously access an application, unless you are a consumer application like ChatGPT.
Sure.
Right, where you get any given instant, you can batch like a 500 or 1,000 users and keep the machine fully utilized, right? That's great, but there's not many applications out there that are like that, right? Where that, first of all, as you said, inference is a highly bursty workload. there's a good chance at any given instant you may not have many users accessing the application. Then what do you do? How do you keep the machine utilized? So I think the way we have built our solution is we kind of saturate at a lower batch.
Yeah.
Right. And that's because we have balanced. We are not over-indexed on compute.
Yeah.
We've kind of said, okay, we'll have the right amount of compute, but we want to balance it with the right amount of memory bandwidth. So there's always data available to the compute. So we can quickly saturate the compute because data is always available to the compute. We may not be able to do it at a very high batch. We'll probably do it at a lower batch. So our goal is in a batch of 100 or less. But most of the applications in the world are probably in that range. People are like, what, customers tell us, batch of 50, 60 is already tough.
Yeah.
For us to kind of find that many users in any given instant to kind of go access the application. So we kind of try to balance these things out. We have not gone off and that's, again, if your DNA is performance, which is what GPU started as a highly performant compute engine.
Yep.
So they over-indexed on compute, and now they kind of try to solve the memory problem by bolting, HBM, which is it's costly, it's power hungry and all that. I think it works for today, but I think for the inference world of tomorrow, I think you need something like what we have done, is essentially kind of find the right balance between compute, memory bandwidth, memory capacity, make sure you kind of saturate compute, not at a super high batch, but there's just the right amount of batching, right?
Yeah.
So it's kind of, we think our solution is very well balanced, right? And pretty much every customer conversation we have, they love that part, right? Is like, wow, yeah, okay, that's great, because enterprise applications, yeah, we couldn't possibly bash, 1,000 people.
Yeah,
right,
sure.
at any given instant, right? And then otherwise you can throw a GPU at the problem, but then it's an overkill. And for a lot of these applications, GPUs are overkills. And I think if I see the Blackwell roadmap and I see the NVIDIA GPU roadmap, it seems like they're going further down that path where they're saying, it's NVL 72, NVL 144, NVL 576. So now you have 500 GPUs that you need to keep fully occupied to aggregate all that memory bandwidth. But then how many workloads and how many users do you need? How big of a workload and how many users do you need to keep those many GPUs fully?
Right.
And how many customers in the world actually need that? And that is a question. So, maybe good for frontier models.
Sure.
And that's where we say, NVIDIA and the GPU crowd, maybe they're very good for the frontier models, and our solutions are sub-frontier.
Yeah.
Right. So we don't want to focus on the the bleeding edge of the frontier, but there are all these distal models and smaller models that have this kind of user profile, and that's what we're going to be focused on.
Cool. Are you going to do an edge version of this? You have chiplets, kind of scalable and very low power.
We could.
Would you go into robots or something?
We could. And we've had people kind of approach us with that interest, like cars,
Yeah, okay.
They say, yeah, we could take this and, slice it down. So we have had car companies approach us. We've had PC companies approach us.
Really?
Yeah. So we could just take one chiplet.
Yeah.
And just co-package it with a CPU and just, can we do that? And that's the beauty of the chiplet approach, because it's not like one big reticle size chip and then, we can actually slice and dice this into so many different markets.
Yeah.
So then it really becomes a business decision, because once you go into these other markets, the software stack is completely different. The call cycles are completely different.
Yeah.
The sales cycles are completely different. And then you need a different sales team for that. You can't have a sales team that sells into data centers also, targeting PCs and, car companies and whatnot. And the company is just not at the stage where we can scale into all these different markets at the same time. So right now we are focused on data centers. Maybe over time, we'll once we feel we have a good position in the data center market and the software is mature enough, we can migrate into some of these other markets. But the platform does allow for it.
How mature is the software from your side? How's that coming along?
It's always a journey, right? It's never mature enough. In fact, if you ask NVIDIA, they say our software is not mature enough, right? We're still working on it. And, with every generation of GPU, they make a lot of changes. And so I think we're making good progress. I think the product was announced in November of last year. So it's been 6 months. Mm-hmm. And we'll have it'd be running here in a month. So, call it in 6 to 9 months.
Yep.
We'll have 8B. And by the way, 8B is, keep in mind, a few years ago, running ResNet or BERT was a great thing. We already have BERT running, by the way.
Okay.
Right. But that was a 5 to 6 month process after the chip came back.
I remember, yeah.
Right. And it was a single chip, single card. Now it's like, oh, wait a minute. You got 8 cards in a single node. You got to take software and, break it across all these cards. And you're getting all of that done in, 6 to 8 months after, chip came back. Right. So I think it's great progress. The team is doing really well. They kind of foresaw that they will have to do these things ahead of time. So they had already started working on it. The fact that we'll have 70B, in a few months after that, I think, within a year of having silicon back. And that's, again, not even a single node now. You're talking 8 nodes in a rack, with scale out and all that. So I think we're making good progress. I wish it was faster, but I think it's fast enough,
So I think one of your key applications is real-time video. Yeah,
Correct.
tell us more about that.
Yeah. So we're very excited about that because so first of all, video models are not they don't tend to be very big, right? I mean, if you look at movie gen, which is something that Meta has announced, like 30 billion parameter model. So that's roughly the size. It's like a sub 50 billion regime, right? And other companies have announced, if you look at Sora or any of these other models, it's not, they don't tend to be very big. Of course, there's no data on how big Sora is, but I think the hunch is it's not a very, very large model like, GPT-4 or something like that. Now, so that's one thing. The other thing is video generation today is not an interactive process, right?
Right.
So you prompt the model, you kind of walk away for few minutes,
get some coffee,
come back, and you don't like what you see, then you kind of reprompt it and you kind of go, this is not going to work for anyone who's right in the business of making movies or influencers who want to kind of, post videos in real time based on, some, location they might be at or whatnot. So how do we make this highly interactive, right? And I think, again, the crux is, it's a memory bottleneck. It's a memory choke point, right?
Yep.
So if you're sitting with an HBM solution today and the model is only a 30 billion parameter model, right? So it is not like you can aggregate, 500, unless you take the model and shard it across 500 GPUs, which is not a great idea either.
Yeah.
Right, to collect all that bandwidth, or then you create a different class of problems. It's better to create a solution like ours, which is contained in a single node. We could run a video model.
Yes.
But we just have so much more memory bandwidth that this actually unlocks. We have 10 to 15 times the memory bandwidth that HBM has, right?
Yeah.
So we can unlock that use case where you can actually interact with this model in real time and make it more interactive, right? And where, it's like you're prompting a model, the model is doing something in real time, and then you can, if you don't like what you see, you can prompt it in real time and it just kind of responds to you. It's more like having a chat.
Yes, okay.
Like more like a video chat. It's almost like, how video gen chat. So we think there is a video gen moment here that will happen in the next year or two, right? Like just as it was a chat GPT moment, there is going to be a video gen moment where this will become truly interactive, and there'll be like an aha for people. It hasn't happened yet because it's just so not usable right now.
Yeah. Okay.
That people just kind of written it off, right? But I think once we unlock this, we think there will be some kind of an aha moment in the next couple of years. If you're like, wow, now this makes a lot of sense, right? I can now actually do a lot with this, right? So we are working towards that to make it happen.
Sounds great. Thank you so much, Sid, for talking us through test time scaling and what that means for hardware. If you want to learn more about D-Matrix and how they're addressing token latency and throughput for big reasoning models, I have an article up on E! Times this week about the company's inference accelerator. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. If you're listening to this on the podcast page at eetimes.com, links to articles on topics we've discussed are shown on your left. AI with Sally is brought to you by Aspen Core Media. The host is Sally Ward-Foxton and the producer is James Eade. Thank you for listening.